Hello and welcome to CS350 online episode number 9. I'm your host as always, Leslie Eisted. And on today's episode, we're going to start talking about processes and all of the different process management calls that we have available to us in OS 161. But first, let's do our segment on the operating system of the day. So, our OS of the day was called OS 360, which obviously is where some of the inspiration for our own operating system of 161's name comes from. And OS 360 was released in 1967, just before Unix, and it was a product of IBM, and it ran on a series of computers known as the System 360, which were generally considered to be pretty successful machines. And if you were to take a look at the title card for our episodes here, the main image of the control panel is actually a piece of a System 360, as is the tape player at the top corner. That's also a piece of the System 360. And another interesting thing about the System 360 is that if you've ever heard of the Red Room that used to exist in the math building, the Red Room actually used to house a 360. That's kind of neat. So the operating system, OS 360, there were 3 levels that were produced, and depending on which hardware you bought, depending on how much money you paid, you would get a different version of the operating system. So the low-level one was called PCP, not to be confused with any kind of hard drugs or anything, but PCP was for users with low memory systems, and you're looking at really just kind of batch processing, the basic tools. Then they had MFT, which gave you, for a fixed number of tasks, it gave you the ability to do multi-programming. Now keep in mind, this is not time-shared concurrency as is offered by other operating systems like DTSS that predates System 360s and OS 360. This is just multi-programming, where when the resource becomes idle, we're able to swap another job in. And then they had MVT, which was multi-programming with a variable number of tasks. Now, you'll note that there was time sharing. It was available in other operating systems at the time. So why didn't IBM offer it? They had tried to offer it, but their implementation was not successful. That happens, and it ended up getting delayed quite some years. And finally, in 1971, when IBM released an update to OS 360, they released with it the time-sharing option. And for a brief period of time, OS 360 became popular again, but it wasn't actually because of the time-sharing. It was actually because of the editor and the debugger that they provided with the update. Now, they actually continued working on OS 360 for quite some time, and later editions of the operating system introduced many concepts which are still around IBM today, such as vSAM, which is a virtual storage access method, which is kind of the basis for a lot of IBM's database systems. So that's kind of neat. All right. So we're not going to talk about what happened in our last episode. That was because we concluded the section on synchronization. But now today, what we're going to do is we're actually going to start talking about a new topic, which is processes. Because everything that we've been talking about so far has been threads, but whose threads? What program do these threads belong to? So now we actually need to come back and talk about the processes or the programs themselves. So if you are following along with the course notes that are provided online, you're looking to get yourself a copy of the process slides, which should look something like this. So what is a process? And, well, if you read the textbooks and you go online, a lot of people will just tell you that a process is a program that's running. But that's actually a very inaccurate description of what a process is. A process is more than just a running program. or a program that's waiting on something. A process is actually the whole execution environment that is created by the operating system for the program to run in. Think of it this way. When we were talking about multiple threads, you had a program that had a bunch of threads. Well, where do those threads live such that they belong to a program? What about the address space? Where does that address space for the program live? So the execution environment is actually all of those things. So it's very common to see these little diagrams here like you're seeing on the screen right now, where the process is this big structure. And inside of the structure, you'll see an address space. And that's going to contain our code segment, our data segments, heaps, stacks, and so on. And then we have a thread array. And the thread array contains all of the threads that belong to this process. Now, interestingly enough, after assignment 1, we're going to go back to a land where every program has only one thread. But we're now just going to allow multiple programs. So thread arrays can, in the real world, contain multiple threads. But for A2A and beyond, all of your thread arrays should only have one thread in them. Now there's other parts of the process structure too, things like a file descriptor table. And what a file descriptor table is it's where we keep track of all of the files that are opened by a particular program and what is our current position in those files. And we'll talk more about that when we talk about file systems in general. Now, this is what you get then. A process is this whole package, this execution environment that is the address space, the array of threads, and all of the access to resources like files and sockets and so on. That's your process. And what's going to happen is when you open a program, your operating system is going to create a process structure for it. And then as you load the program, you are going to be creating the address space and loading the data from the binary file into the address space, creating the threads for the program, and so on and so forth. And then when we finally run the program, we're going to be choosing one of the threads and moving it from ready to running. So what I'd like to do now is let's switch over here to a terminal. And I don't think you guys want that one, so let's go to this one here. So I'm in the kern directory. Make this a little bigger for you. And I'm going to go into include. And didn't mean to hit that. We're going to open proc.h. Now my proc.h has been filled in a little bit, so you're going to see some stuff in mine that's not in your proc.h. But let's go in there just for the sake of discussion. So if we go in, what you're going to see, again, there's some stuff in here that you won't have. But the stuff that you would have, just for the sake of discussion, let's make this smaller. You're going to have this basic proc structure. And inside the proc structure, you're going to see a few things. You will see the name of the process. You will see a spin lock for the process. You will see an array of threads, the thread array. And by the way, if you're looking at the thread array, it's using the array type that's included in the kernel of the operating system. And then we have a pointer to the address space structure. Now there's a bunch of other stuff here. You don't need to worry about it because it's not there for you. If you were to open up a raw copy of proc.h, you wouldn't see any of those other fancy things. So the process structure as it stands right now in OS 161 has some of the basics, but it's also missing a lot of pieces. For one, and we'll talk about this a little bit later, is that we don't generally identify processes by their names because there's never a guarantee that the name of a process is going to be unique. For example, I can open up MATLAB on my computer 100 times, and each time I open it, it's going to be called MATLAB. And the way that I instantiate the program is going to be the same. So that's not going to give me any additional hints either. So we don't usually identify processes by a name, but by a unique process identification number, a PID. And you will note when you open proc.h that the proc structure is missing a PID, and that's one of those many things that you're going to have to be adding for the next assignment. Now, we have this process structure in here. How does the operating system keep track of all of these? Well, it's different for each operating system, but it's very common for most operating systems to actually keep track of a table of all their operating systems and the states, or all the processes and all their states. So operating systems typically have a process table of some kind because we want the ability to find out what is the current status of particular processes. I want to keep track of how much resources has each process been given. How much resources is a particular process using right now? I want to be able to know all of this information in the operating system about each of the processes that are running, and so we usually keep a process table. Now, how that is implemented really differs OS to OS. Something else that's really interesting about processes is that they're going to be used to actually isolate programs from one another. Now, what does it mean to isolate a program from one another? Well, let's think about it this way. So EA has just released, or is in the process of releasing, a remastered version of the C&C games, the original C&Cs. So let's suppose you buy Red Alert. I haven't played Red Alert in probably 25 years. I much preferred Red Alert 2, but let's suppose we play Red Alert. And I'm going to play as a Soviet country, and I'm going to start building some apocalypse tanks. I don't remember if they were in the original one or not. Now, supposing I build some of these tanks, and I start clicking on the button, each of the tanks cost a certain amount of money. We don't want the Red Alert process to magically open up Chrome process, go to our bank account, and instead of deducting game money, start deducting money for apocalypse tanks from our actual bank account. We don't really want processes to be able to directly communicate or impact other processes. We don't want one process to be able to start writing into the address space of another process, because that's going to cause race conditions to happen between multiple processes. And that's just an absolute nightmare of a situation. So we use these process structures along with virtual memory to help provide some isolation so that the processes aren't directly impacting each other. Now, does that mean you cannot have two processes communicate with each other? No. It is actually permitted for processes to communicate information between each other. However, how this is done has to be through different mechanisms provided by the operating system. I can't have process A directly call a function in process B. We don't permit that. But what we do permit is process A to write to a file and process B to read from that exact same file. Now, that's actually a very bad way of doing this, but it's doable. These methods of letting processes talk to each other are called IPC, or inter-process communication. And we'll discuss them very briefly at the end of this module. So what I'd like to do then is talk a little bit about process management on a Unix-based operating system. Now, keep in mind, if you're using Windows, you can try a lot of these commands in the bash interface, but the native Windows commands for process management are a little bit different than what we're going to do. So let's go back then to a terminal. And now that I've got a terminal up, the first thing I want to show you is the top command. Now, I'm sure many of you have actually seen this, but let's hit top here. Now, on a Mac, this shows me a slightly different set of things than this would on, say, the school's Unix servers, but it still shows the basics of what I want to do. So first off, at the very top, you'll notice it tells me how many processes in total are on my computer. There are 491 right now. And between 2 and 5 seem to be running. What does it mean for a process to be running? Well, a process running means at least one of its threads is executing instructions on the CPU right now. Which leads me to the discussion that processes have states, just like threads. Processes can be running, processes can be ready, processes can be blocked. They can also be terminated, and they can be zombies. Now, a zombie process is one who has data still lying in the kernel, but isn't actually capable of running. That's not going to make a lot of sense right now, but we'll be dealing a lot with zombie processes later on. So looking at this, I have 491 processes, but between them only between 2 and 5 ever actually run. It also tells me, of course, how many threads I have in total, which is over 2,600, and 488 of them are sleeping. That is, they're waiting for some kind of input. Oh, I had a stuck. So we have a question here on Twitch, and the question is, how do programs like cheat engines or other memory editors hook into another program then, if processes have to communicate through a file or other OS-defined interfaces? So I actually don't know too much about a lot of cheat software, but the one thing I can say is, even though processes and virtual memory are designed to isolate one program from another, that doesn't necessarily mean that we are 100% successful at doing this, because obviously hackers are able to read memory and get information off the stack and so on and so forth. And I'm guessing that some of these cheat programs actually work like that. And I think some of these other cheat tools also may create parent-child relationships between the cheat program and the game program, which gives us a little bit more flexibility than just any two random processes. And there's also the possibility that the game program has been altered in some way to permit the cheat program to work. But again, I don't know much about how those actually work, so I can't talk directly about it. And I think there's also a lot of variation in how they work as well. All right, then. Now let's look at some of the other things that top is showing me. So what you'll see here is in the table below, it's actually listing the processes. Now, obviously, I have 492 processes. You're only seeing the ones that are using the most amount of my CPU at this time. Now, you might be a little confused because you're seeing the percentage of CPU use is obviously adding up to more than 100. And the reason, of course, for that is that my MacBook Pro here is an i9. I have 6 cores, and each of those cores can have 2 threads running in parallel. So I have a lot more CPU power than just 100%. All right, so what we're seeing here, so OBS right now, which is what I'm actually using to do the streaming and the recording, is process ID number 84,470. And if we search, we'll note that there's no other process on the system right now that is using that unique PID. PIDs have to be unique. Names don't. So we keep track of how much time it's using, or how much CPU power it's using, how long it's been running, how many threads it has, and how many of these other things that it has. So how many ports it's using, how much memory it's using, and so on and so forth. So there's lots of information that top is telling us about a particular process. Now, what's interesting about the top program is how you can actually use it. So say you log on to a school server and it's behaving really, really poorly. And you want to know, why is this machine behaving poorly? Well, what you can do is you can open up top and you can look at all the processes running. And you can take a guess and say, okay, well, of all of the processes that are running, I see that there's this particular user who appears to be mining Bitcoin, and they're using almost 100% of the CPU resources and a significant amount of memory. So you can use top to kind of diagnose what's going on with the system right now. It's also good for, let's say you have an infinite loop in a program or infinite recursion and you need to identify the process. It should be noted right at the top, and then you should be able to just grab the process ID number of it, and then you can terminate it. Now, how to terminate a process is using the kill command. So for example, if I wanted to just kill some random process, I could do kill and then there's some PID. I don't know if that's a PID that's in use or not. Now, sometimes we need to kill processes with fire. That is, shut down, not nicely, just kill this thing. And that's where we use the -9 flag to actually kill the process. Just get rid of it, terminate it now. It's not always necessary to use that -9 flag, but I always use it. All right. Now, here's some other interesting tools out there. So top's going to show you things like which processors are using the majority of the resources on your system. But let's suppose that you're in Chrome, or let's use Chrome in particular here. And Chrome's interesting because each of the tabs in Chrome are actually using separate processes, which has some interesting advantages. In particular, because each of the tabs are separate processes, and then they can communicate through different IPC channels, of course. But since they're separate processes, if you have a tab in Chrome that's misbehaving, you don't actually have to shut Chrome down as a whole. You just terminate the tab that's misbehaving. So if you've navigated to maybe a rather seedy website and a little pop-up shows up and it says, click OK or cancel to continue, and you know for certain if you click anything, you're going to get a virus, and it's not going to let you click the X on the tab button because it wants you to deal with the pop-up. So you're like, what am I going to do? I've got my Learn quiz for 8 of my other courses open in all the other tabs, and I've got a chat open with somebody else in one of those other tabs, and if I kill Chrome, I'm going to lose all of those things. So we actually have the ability to search for the ID of the specific process and learn information about it. So let's suppose you had gone to a seedy website, because that's how you usually get these pop-ups. So I want to search for Chrome processes. So I can use this PS command, and I'm going to pipe the results to grep. I'm going to search for processes where Chrome is the name. Now, you'll see here, these are all of the Chrome processes that are running on my computer. And yes, there are a lot of them. So what's interesting is what you're seeing here is this is the name of the process, but it's also, you'll see all of the command line flags that were given to it when the program was instantiated. So those are all of our command line args. And then beside it, you can see what the PID number is, and you can usually see something about the state. Just kind of neat. Now, what you would do then, supposing you wanted to, and I'm not actually going to kill it this time, but what you would need to do to kill the process is you find the tab or the process here that has the pop-up. And I want to tell you that it's very obvious because all of the command line arguments will be a bunch of gibberish. And like just symbols, pluses and minuses and things like that. It's usually really obvious which one is the bad one. You take note of its PID, and then you do kill -9, that PID, and bam, the bad tab that's going to give you a virus is gone. So those are 2 of the basic process management commands that you have at your fingertips in a Unix-based operating system. And there are, of course, many others. For example, we have the nice command in Unix, which is going to set the priority or the weight of different processes. So if you want to be nice to your fellow users, then you will lower the weighting of your particular program you want to run so that everybody else can have a little bit more time on the CPU. And there are many others. So there's kill, there's a list. And we'll actually show you this list here in just a minute. So going back then, here are some of the specific process management calls that are out there. So to create, one of the things we didn't talk about is how to create a process. Well, there are many ways to create processes, and they really vary by operating system. But in Linux, there are two primary ways that you can create a process, and that is to fork or execy. And OS 161 also has those same two. Then we have, how do you destroy processes? Well, you already saw one way to destroy a process, and that's using the kill command. But what if you want to kill the process that's running right now? Then you can use things like the exit command. Now, Linux has both of these commands, but things like OS 161, they only offer the exit command. Then we have process synchronization. So it is quite common, actually, for some programs, things like Chrome, to take a task and instead of dividing it across multiple threads, they'll divide it across multiple processes. And one example actually of something that gets divided into multiple processes is actually things like MapReduce and Hadoop. It's common, I think, for people to see it done as threads, but on AWS, it's also done as processes. And here's the idea. You're going to have some master process. The parent is going to subdivide the work, and then it's going to fork off a new process for each of its workers and pass to each process the work they need to do. And then before the reduce phase can happen, the parent needs to be able to wait for all of the child processes to complete before it can aggregate and reduce the result. So in order to permit synchronization between processes, to force one process to wait on another, there are a whole pile of synchronization commands offered by Linux and Windows and so on and so forth. And these are also used for things like IPC, because IPC does actually require some synchronization, especially if you're doing something like IPC over a file or IPC over a shared memory block. So we have a question that says, can we use the term concurrency for the processes which are running at the same time? Yes, it's also often referred to as multiprocessing, which is the ability to have multiple processes running at the same time. Now, so we've got creating processes, we've got destroying processes, and we've got synchronizing processes. We also have the ability to get information about the process. And you should have been thinking about this, because that's what TOP was doing, is TOP was looking in the process table that the OS has to get the information about all of the processes that existed and then displaying it to us. So there's commands like getpid, getuid. That means usually get the name of the user that created this process. I talked about nice as being able to set a process's priority, to set how much of the CPU does it get on average, get usage. There's many, many different attribute management calls for processes in Linux. And in OS 161, the only thing we have is getpid. Now, when I say OS 161 has these 5 process management commands, what I'm actually saying is you're going to implement them. So A2A and A2B is you actually implementing these 5 commands. So let's actually take a closer look at what these 5 commands actually do then. So as I said, fork is one of the things that's going to be used to create a new process. Now, when we create a new process, the person who called fork, or the process that called fork, we call them the parent. And the new process that was created is called the child. So we have these parent-child relationships between processes, which is not something that we would typically have between threads. Now, what does the child process contain? Like, what is its address space? What's its thread array? Well, here's the interesting thing. When you call fork, the child process is a new process. It is a separate process structure with its own PID, but the program is identical. So the address space of the child process is the same as the address space of the parent process. The stacks of the child process, therefore, are the same as the stacks for the parent process, which means that the parent and child process will be executing the exact same program from the exact same position in code. So both the parent and the child process are going to return from fork. Now, there's one teeny difference that we use here. The parent, when it returns from fork, fork will provide to the parent the PID of the child process. The child, on the other hand, gets as a return value from fork 0, indicating you're the child. So, other than that, though, the two processes are identical when they return from fork. Now, what that means is that anything on the stacks is the same, anything in shared memory was the same, they're all the same. But after the point of forking, if the child process goes and executes something else and changes stuff in its memory, that's not going to impact the parent, because from the point of the fork, they start out the same, but they are separate and they're not impacting each other anymore. Okay, so that's what fork does. Then we have exit and wait PID. And these kind of have to be discussed together. So exit is going to terminate the calling process, which means that if that process has any number of threads, they're all going to be killed. Well, terminated. And then the process itself will be terminated. Now, one of the things that you're going to note is that the exit command in OS 161 and in many systems takes an argument. And that argument is an exit status code. It's a little bit of information that you can pass from the terminating process, and you can keep it around in the operating system for the parent if you choose. Now, what this means is that when you call exit, if your parent is alive, that is, they are still around, not necessarily running, but they're still either ready or sleeping. If your parent is alive, then we're not going to fully delete you, and we turn you into what's known as a zombie. So you're terminated, you are dead. You can't run anymore, you're not alive, but we're going to keep your body around so that we can figure out why you died and conduct an autopsy, so to speak. So that exit status code is going to be stored in the operating system in some way should your parent still be alive. And how that information gets used is through the waitpid synchronization command. What waitpid lets us do is it lets one process wait for another process to terminate. And why we would want to do that is maybe we have a parent has created a bunch of map workers as processes, and they've all gone and done their tasks, and now the parent is waiting for the maps to finish so that it can do the reduce phase. Well, it needs to call wait to wait for each of those processes to terminate. And then once it has waited for all of those processes to terminate, it needs to check before it does that aggregation, the reduce phase, that each of those processes actually terminated successfully. That is, they actually terminated without an error. And so we want the ability to figure out, why did the process die and how did it die? So the exit status code is one piece of information a zombie has, which is passed from the process itself. The other piece of information we have is, did the process die due to a call to exit? Did it die because it was killed? Or so on and so forth. So we have two pieces of information, which after calling waitpid, we can get that information, and then we can determine if, say, we can do the reduce phase of our code. So exit and waitpid really work together. Now, before we go on to the next slide, which has an example of using these, there's one more thing I want to say about waitpid. Waitpid, in OS 161 at least, can only be used on your child process. You are only allowed to wait for your children to die. You are not permitted to wait for your parents to die. You are not permitted to wait for your grandchildren to die. You are not permitted to wait for your cousins, your aunts, your uncles, or any other random process to die. The only processes that you can call waitpid on are your children. Now, here's a question I get asked every single term. What happens to the child process if the parent terminates? And while it might be morbid to think about, but it is a good example, if your parent dies, what happens to you? You are an isolated, separate being who goes on living. You might be very sad, but you're going to go on living. And the same is true for processes. Parents and child, we keep track of that relationship, but the two processes after the point of forking are separated from each other, such that if the parent dies, the child is going to keep on running. And similarly speaking, if the child dies, the parent process is going to go on living. Now, when a process becomes an orphan, that is, its parent is no longer around, we don't then take that orphan and assign it a new parent. So we're not going to take the grandparent and say, here, grandparent, you now have to take care of your grandchild. No, there's nothing like that. If you are orphaned, you are orphaned. And that's the end of the story. So let's look at a little example here. So we have a little bit of code. Now this is pseudocode, of course. And somewhere inside the code, we're going to call fork. Now that's going to, create a new process with a new PID, but the contents of the address space and the stacks and so on are going to be the same. So I now have two processes. They're both running this program, and their program counters are going to be at an identical position in the code, which means they are both going to return from fork. Now the child process, remember, would have the return value from fork be 0. So if we have this if statement here, that means only the child process will execute this code here. And then the parent, who gets the child's PID returned from fork, would execute this code here. So what we're going to have is the child gets its own PID. Does some work, and then it calls exit, and it passes this exit status code along, which will, so long as the parent is alive, this will be stored with the zombie until the parent does the autopsy on the child. Now you can use this exit code to store data. You can use it to indicate an error code from the program. Typically speaking, an exit status code of 0 means we terminated successfully. And that should be something you're fairly familiar with, because you should know that when you return from main, you want to return 0, because 0 is saying I terminated successfully, and anything else would be I did not terminate successfully. Now our parent has the PID of the child. We're going to store it here in child PID. We do some work, it doesn't really matter what we're doing, and then we decide we're going to wait for the child process to terminate. So we're going to call waitpid, and we are going to pass it the child's PID that we got earlier. And then this child exit, this is where we are going to store both the exit status and the exit code. And it's two integers combined into a single one. And we'll talk more about that, how that works another day. So what's going to happen then is in waitpid, if the child process has terminated, that is, it's already dead, then we're going to retrieve its exit status code, delete the process completely, so get rid of the zombie, and then we're going to return from waitpid with the exit status code and the exit code from that zombie process. If, however, when we call waitpid, our child process is still alive, then the calling thread, the parent, is going to block. And it's going to block until the child terminates. And when the child terminates, the child should wake its parent back up so that the parent can then grab the exit code. Once, regardless of whether we have waited for our child to terminate or our child was already terminated, at this point here, we know that child exit contains both our exit code and our exit status code. And OS 161 has several built-in macros that you can use to extract how it exited and what the exit status was. So if exited is going to return true if the child process terminated because it called exit. And we know it did because that's what we were doing in the child process. So now we're going to use this other macro here, exit status, to get the value of X from here. So there you go. You have one program where we started out with one process. We called fork. The two processes then did some different work, and we let the parent wait on the child. And again, you could modify this code very simply to turn into something like MapReduce, but with multiple processes. All right, now let's talk about execy. Sorry, if you see me scrolling around all kind of funny, I always forget to put my mouse wheel in the correct scrolling mode for this. All right, that's 3 of our process management calls that we have. We haven't talked about getpid. I don't see a point in dedicating any slide to getpid. Getpid returns the PID of the process that called it. End of story. You're going to implement it. It's going to be like one line of code. It's not worth talking about. But it is worth talking about execy. What execy does is it changes the program that an existing process is running. So if I had a process that was running MATLAB and I called execy and ran Minecraft, I'm not creating a new process structure. I have the exact same process structure that I had before. My PID does not change. But my address space, which is the program, and the thread array is going to change. So we can call execy to change the program that an existing process is running. And of course, since we're going to change the program the process is running, we're going to need to pass some information to execy, such as what program do you want it to run? And what are the command line arguments for that program? So here's an example of using it. And this is actually from the tests that you will have available to you. And it is, I think this is arg test. So what we're going to do is we're first going to build our argument array. Oh, excuse me. So it's very traditional for the first argument to be the name of the program you're running, which is what we've done here. And then we've got some other arguments. This is just how they've decided to set this test up. So when we call execy, we're going to pass the name of the program we want to run, and then we pass in the array of arguments. Now note that the array of arguments is stored as an array of pointers to strings. Now here's the thing. When I call execy, I don't return from execy if I succeed. So that's what you're seeing down here. Printf, if you see this, execy failed. Why is this here? If execy succeeds, the program that called execy stops running. And the new program is loaded and starts running, which means execy can't return because there's nothing to return to because it's deleted, it's gone. So if execy succeeds, you don't return, you just start running the new program. If execy fails, and it can fail for various reasons, that is the only time where execv would actually return. Now, what this means is when you call execv, what you're going to have to do is you're going to have to load the new program into the address space. But that's not really making sense, because if I was running, say, hello world, which has maybe a 1 kilobyte address space, and I all of a sudden call execv run MATLAB, which has like a 5 gigabyte address space, I can't copy the 5 gig address space of MATLAB into the 1 kilobyte address space created for hello world. So when we call execv, we're keeping the process structure, we're keeping the PID, but we're going to have to make a new address space and cop for the new program, because the new program probably wouldn't fit into the old one. So that's why when you actually call execv, the old address space doesn't exist. It's gone, it's deleted. You can also use this in combination with fork. So here we have our fork. We're creating a parent and a child. And after I create the parent and child process, I'm going to have the child process call execv and run a different program. And then the parent is going to wait for the child process to terminate. Which brings up an interesting point of discussion. When you call execv, the process structure remains the same. The PID remains the same. Only the program changes. Something else that remains the same is the parent-child relationship. You can call execv 1,000 times, and it doesn't change who your parent is. It's like in real life. If you go out and you dye your hair fluorescent green, and you carve all kinds of patterns into it, your parents might hate it, but they're still your parents. Your parents might disown you, but they can't actually change the fact that they are your parent. And the same is true with processes and execv. It doesn't matter how many times you call execv. It doesn't matter what program you are running. Your parent is your parent, and that does not change. All right. So what I'd like to do then is, before we discuss this slide, I'd like to open up a sample problem. And if you're sitting at home there, this is a 2-part sample problem. And I think I'll do one part of this today. And maybe we'll do the other part tomorrow. So this is proc fork, which you will find, of course, in that folder or that zip archive that's posted to Piazza. So we have this little bit of code we're going to call fork, and we're going to do some printing. So the question is, what is going to be generated by the parent program, and what output is going to be generated by the child process? Now, before I do that, we have a question on Twitch that says, what happens to the program that was in the process before we run execv? Does it become a zombie? No. A zombie is a process that has terminated and is not running, but has left some data behind in case its parent wants to check why it died. When we call execv, we are not creating a new process. We are just changing the code that the existing process runs. So we are destroying the old address space and giving the process a new address space. So there's no zombies created there. All right, so let's actually... Sorry, my tablet here is telling me that it has a low battery, so hopefully this will survive this. So let's open up OneNote. So looking just at this problem here, I want to know, we'll do this part today and we'll do part 2 tomorrow. I want to know what is the parent going to print and what is the child going to print. So the first thing I note is that x starts out at 0 and x should be 0 at the beginning of both the parent and the child. So at the point of fork, x is equal to 0. And then we get this branching behavior. So our parent is going to go one way and our child is going to go another way. And that means that the parent is going to have its own copy of x equal to 0, and the child is going to have their own copy of x equal to 0. Now keep in mind, this one is actually this one down here. So now what we have is the child process is going to then set x to 10. Not 110, just 10. And then it's going to print AX. And then it's going to print CX. So what we're going to get for the child is A10, C10. But if we look at the parent, you'll see here x is 0 and then it prints BX. Changes x. So we're going to get, oh, that's nice. We're going to get B0, and then we set x equal to 100, and then we're going to print CX, which gives us C100. So there you go. The parent process will print B0, C100, and the child process will print A10, C10. Now, part B, I will let you spend the next day working on it, and then we'll take up the solution to this in our next class. But what we have here is a little function with 3 forks, and we'd like you to draw a tree to represent all of the new processes and how they were created by fork. All right then. Now, we've been talking about these process management calls. Oh, question. So do we know which process will print first? No, you don't. And you can't know that. And you don't know if it's going to be process A prints, process B prints, process A prints, process B prints. You don't know that. And the reason why you don't know that is because you have no control over the order which threads execute. And remember, it's not actually processes that are executing, it's the threads of the process that are executing. And you have no control over the context switches. So you cannot know for that particular program what order things are actually going to print out in. Another question here is, would there be a way to modify a variable in the child code and have it be changed in the parent process? So without IPC, no. So for example, let's suppose I changed X in the child and I want to reflect that change back to the parent. I would have to have the parent use some kind and child use some kind of inter-process communication mechanism, which would go through the operating system in some way to actually facilitate the parent getting the updated value. But that is not, the child changing its memory is not going to directly change the parent's memory. You would have to use IPC or some mechanism like that to make that change. All right then. These process management calls that we have, like fork and execv, are actually things, part of a bigger group of things. And that bigger group of things is called a system call. Because things like fork, we are asking the operating system to do something for us. We are saying, hey OS, I want you to make me a new process. Make me a clone. When I call execv, I'm saying, hey OS, change the program this process is running. So system calls are a set of functions, it's a big set of functions that we have available to us to ask the operating system to do something on our behalf. And these are things that you actually have a lot of experience with. So for one, we've just talked about all of our process calls, but if you have ever opened a file, read a file, written to a file, which I promise every single one of you have, even if you haven't written the code for, in order to read and write and open and close files, you have to ask the operating system to do that. And the reason why you as a user have to ask the OS to do this is because the kernel, if you remember, is what stands between the hardware and the user. The kernel is abstracting the hardware and the implementation details underneath so that the user and the user programs don't have to know anything about it. And as part of that abstraction, the kernel is providing to us these system calls so that we can call open and it just opens the file. And we can call write and it just writes to the file. And we don't have to know that the file was on a magnetic tape at the university. And if you're sitting there laughing like, ha ha ha, nobody uses magnetic tapes anymore, you're wrong. And in fact, the university also still uses magnetic tapes. And we'll talk more about why when we talk about file systems and disks. So opening and closing files, we're asking the operating system to do something for us. Making directories, linking, shares, interprocess communication, sending data from one of these processes to another, networking commands, things like managing memory. So let's say you want to increase your heap. Let's say you want to increase your stack. Those commands are all system calls. Rebooting, getting the time. They are all system calls. They are all these abstract functions provided to the user to get the kernel of the operating system to do something for you. But here's the thing. I really, really, really want the operating system, the kernel, to be isolated from the user. So we have this thing called a system call library. And that is stuff. Sorry, laughing. Twitch comment. This comment is that's why the CS servers have been so slow. No, but we'll talk about why the CS servers, why the CS department is using tape drives later. The primary active servers use actual disks. We're using tape storage for archive. Anyways, back to the discussion at hand. So we have a system call library. This is what your user applications are going to use to interact with the kernel. So your application wants to write to a file, so you call open. Open is provided by the system call library. Open is going to cause some kernel code to run. It's going to open the file and it's going to return some data back to the system call library, which will format the output and return it to the user application. But as I said, we really, really want that kernel to be isolated from the user in all ways. And what's interesting is this system call library lives up in user land in what we call unprivileged code. And the kernel lives in a privileged area. And this dashed line is not just for decorative purposes. I do not want anything above this line to know anything about what is below this line. I want them to be completely isolated from each other. I want to have the abstraction such that if I modify the kernel, I don't have to modify the things that sit above it. So what's really interesting is I said that the kernel is providing you these system call functions. They're not. The kernel doesn't provide the user or the system call library any API. There is no data structures provided by the kernel. There is no API of functions that are provided such that user applications can call. None of that exists. Because here's the problem. Let's suppose that a user application had access to a kernel's data structure. Let's suppose this dashed line didn't exist. Well, what happens if we need to modify the kernel in some way because there's a security flaw and we have to change that data structure? Well, then I have to change my user applications that use that data structure because the data structure has changed. What about, and the same is true for function calls. Maybe I provide an API directly to the kernel so the user can directly call kernel code. Well, what if I need to change that for security reasons? Well, then I have to change my user program. From an abstract design perspective, this doesn't make a lot of sense. But we also really don't want users to know what the kernel is doing. Because if they know what the kernel's doing, then they have the ability to maybe do things they shouldn't be doing. Make the hacker's job easier. So we want to further isolate the user from the kernel. This dashed line here is not make-believe. This is not an arbitrary thing. This is not just a diagram. This is a CPU mode. CPUs actually have different privilege levels. Now, our CPU, the R3000, has 2 privilege levels that we can use. We have unprivileged mode and we have privileged mode. When we are executing kernel code, we will run in privileged mode. And only kernel code can run in this way. The user program runs in unprivileged mode. And if while we are in unprivileged mode on the CPU, we try to access memory in the kernel, we won't be allowed to, because in unprivileged mode, we can only access certain addresses. And the kernel is going to live in certain other addresses, which are only accessible from privileged mode. So the user program cannot directly access the kernel. We'll talk more about that in virtual memory. All right, so here's the cliffhanger, so to speak. If you, the user, cannot access the kernel's data structures and you can't call the kernel's functions, then how do you actually make the kernel do anything? Well, we've already talked about privilege here. The way that you're going to do this is through interrupts and exceptions, because the only thing that you can do to make a kernel code run is have an interrupt or have an exception. Remember that interrupts are going to be things that were raised by hardware. So an interrupt would be if I pushed on this little Wacom pen, if I pushed the button on it, that would cause an interrupt to be fired. The interrupt would be received, it's a signal received by the CPU. The CPU, upon receiving that interrupt signal, would stop executing your program. We should remember this from our thread section. We stop executing that program. We start executing the interrupt handler whose address is stored in the trap table. Then we're going to save the trap frame, which is the state of the running thread at the time of the interrupt, and then we can actually execute the specific interrupt handler for the pen or whatever thing has happened. That interrupt, when it happens, that is going to cause the CPU to flip from unprivileged mode into privileged mode and permit us to actually execute kernel code. So, exceptions are another way that we can force the kernel to execute the code, some kernel code. Now, exceptions are different because exceptions are not caused by devices. Exceptions, in our case, are actually caused by software executing. So, for example, if you have a division by 0, that is going to be an instruction level exception. The CPU doesn't know how to handle it. The exception gets raised. The CPU then has to flip into privilege mode and tell the exception handler to run. to have the kernel of the operating system handle the fact that there's been a division by 0. And the same is true for executing illegal instructions, page faults, memory things. All of those things are going to raise exceptions that flip the CPU into privilege mode, and then we start running the exception handler to figure out what exception has been raised and how do we recover from that particular exception. So this is the only two ways that we can actually get kernel code to run: by an interrupt or by an exception. So we've got to choose one of these two mechanisms in order to actually get our kernel to do something like open a file. We're not going to use interrupts though, because that doesn't make sense. Interrupts is for devices specifically firing signals that say, hey, do what you need to do. We're going to instead make use of exceptions. And there is actually a special instruction on MIPS and in many architectures for raising exceptions. And you can actually call this as a user program. But simply raising the exception isn't enough, because what are we going to have? One separate assembly instruction for each type of exception we want to raise? Okay, this is the exception we call to open a file. This is the exception we call to send a network packet. That doesn't make sense, because the number of different system calls that we might ask the kernel to do are going to be changing as operating systems change and grow. So it doesn't make sense to update the architecture each time we update the OS. So instead, we have a singular assembly instruction used to raise the exception, and that assembly instruction simply has arguments that are going to be passed into the kernel that will tell the kernel what exception has been raised and what system call are we asking you to perform. Now, before we go into details of how that works, some of you might be familiar with the Meltdown and Spectre vulnerabilities. And if you're not, I will actually post the papers to Piazza. I actually find them to be very approachable. But Meltdown vulnerability, I think this has been out for 2 or 3 years now. But what this was there is this way to actually bypass the execution privilege on the Intel CPU such that a user program could get access to any address in physical memory. And essentially what was happening is, because the CPU, and you might recall this from the last segment of the course, because the CPU actually reorganizes instructions to improve performance, sometimes some of those memory reads or writes, typically reads, were happening for kernel code before we had made the flip. So what would happen is the CPU would do the read, put it in cache somewhere, and then when it was time to, when it actually flipped the privilege, it would check to make sure that was a valid operation or not. But the problem was the space in between there. If you did a cache attack, you could get the data that was kernel privilege out of the cache while you were still a user. So the Meltdown vulnerability effectively bypassed all of the CPU privilege nonsense and let us get whatever memory we wanted. And they have obviously made, this is a pretty serious flaw, which they've made many changes to their architecture since then, patches and so on. However, it has caused, at least according to a lot of the benchmarks, fixing the Meltdown vulnerability has caused a pretty significant impact on the performance of the CPUs. Now, Intel is arguing that it was less than 2%, but there have been some benchmarks that have shown it's as high as 26% reduction in performance. Probably depends on the kind of task that you're doing. Anyways, I'll post the papers. Again, if you're not a security person, if you've never read any deeper OS papers, don't be afraid to read these. They're very, very approachable papers. All right. So back to the discussion then of how are we going to get our user program to cause kernel code to execute. Now I said we're going to have to use exceptions, and we're going to have to pass with the exception some arguments to let the kernel know what exactly we want it to do. So this is the point where I have to tell you that on the MIPS system, we actually don't differentiate between exceptions and interrupts, or at least the CPU, the architecture, doesn't differentiate between the two. Everything in MIPS is actually an exception. And this slide here actually shows you all of the different exception types that there are. And if you'll see here, we have the first exception is of type interrupt. So we actually have interrupts as a subclass of exceptions. And then all of the rest of them are true exceptions. So you've got things like TLB miss on load, TLB miss on store, which some of you have probably seen. And I will post to Piazza exactly what those are should you encounter them. Those are your memory faults, by the way, your seg faults. Then we've got things like bus errors, and we've got breakpoints. That's obviously for the debugger. We've got arithmetic overflow, illegal instruction. And then number 8 here, exsys, is the system call exception code. And if we use the syscall, which is an instruction, it's going to raise an exception of type exsys. So that when the interrupt handler runs, or the exception handler runs, it will see, oh, the exception is of type 8, therefore this is a system call. And then from there, what we're going to do is we're going to get our arguments to tell the kernel exactly what it needs to do. And I'm actually going to leave that there for today. So let's, what we'll do is on Thursday's class, we'll look in greater detail about how we're going to use the system call instruction to tell the kernel specifically which system call we'd like it to do. We're going to also take a closer look at the stacks of the kernel to see what happens when you raise an exception of type syscall. And we're also going to look at what happens when you have preemption happening while we are actually trying to do these system calls at the same time. And then the hope is that at the end of Thursday's episode, you should technically have all of the information you need to do assignments A2A and A2B. Now, that being said, we usually do a lovely A2A guide and an A2B guide, and I will make sure those get posted to Piazza shortly as well. So we will see you on Thursday then.
You wanna start small, but think tall. That's your plan with computers that can grow along with you.
How are you gonna do it?
Well, you're gonna PS to it.
With the IBM PS2.
You wanna network up and network down. Share information with other towns. A well-organized team. Well, that's your dream.
How are you gonna do it?
How? You're gonna PS to it.
With the IBM PS2.
You wanna juggle 10 things all at once and still have time to break for lunch. Woo! In your business, you got a bottom line mission. You got to rise above all the competition.
How are you gonna do it?
Easy. You're gonna PS to it.
The solution is IBM. The solution is IBM.